对吧？大家都这么认真防疫。总之，我先把这看一下。
很多。
今天的确是还蛮多的。今天预计是要把第4章教完，但是有很多有趣的事情。哦，有一位同学来了。
要来上课了。哦，要上课。
是应该要上课啊，可是好像大家都那个。
顺便拿作业。
Okay, more people are here.
还是我那一组，去上课走。
Anyway, okay, so we still have people in person here. Wait. PowerPoint slideshow. This. Okay. Hopefully, wait. Okay, so we have our TA checking the. Do you see a chat room? Okay, maybe we'll have a chat room. Okay, we have less people in person now. What? Excuse me?
Condition.
I think we can do without AC. It's not too hot. Yeah. 就应该不需要冷气吧？
空调应该还好吧？还有窗户。
要开个窗户，虽然会有蚊子。OK， 但是
关个门，因为风大。
风应该是还好，可以让理论上通风比较防疫，是不是？Anyway, okay. So people are very careful about the COVID situation, which is nice. But okay, so organization saying we are still going to have our midterm in person, hopefully. Yeah, the COVID situation is changing very fast, but the school policy right now is still will have in-person test. So we should have in-person test in 2 weeks, which is May 13, I believe. And the range will be chapter 3 and chapter 4. Yeah, and but as you can see, everything is built from chapter 1 and chapter 2. So you probably want to still remember what's being taught there. Yeah. So that's the idea. The idea is we'll finish chapter 4 today, and the first chapter for homework will due next Tuesday, and there will be another chapter for homework due on next Tuesday, and next Friday will be the midterm. So any question for 2 of you here, or do we see chat room? Okay. So the TA is checking chat room. So for the online people, if you tap there, we can probably see. Are people trying? No. Okay. Anyway, hopefully you are online. But okay, let's go back to our class. Today is quite exciting. We are going to teach you an interesting part of the course. Let's small review. So we have been talking about this Fourier transform. No, not this one. Fourier transform pair, which is those 2 equations. This is the most important thing in chapter 4. And we're talking about lots of other properties, and we're talking about sort of boring ones, linearity, etc. And this time we go over this differentiation. Oh, okay. So one thing to correct. So differentiation and integration. So integration is this weird term, and I checked more after class last time, and this is indeed correct. Although the derivation is a little weird, but anyway, bottom line is this equation is correct, and you can use it. Yeah. But you need to be a little careful. So there is this, there is this boundary of minus infinity in terms of integration. But anyway, if you write down everything in this equation correct, that will be the correct equation. Yeah. So we have this differentiation, integration property, and duality, time shifting, etc. And they are nice. Oh, and we also have this possible relationship, which has this 1/2 pi as normalization, but yeah, you just need to remember the form, and well, for the midterm you can probably have the cheat sheet on your side, and you should have this formula. And the idea is energy preservation. So that's from this time. Any question? If not, okay, let's go to an interesting thing. Convolution property. So we're going to be hinting about this every now and then. That is, we have this property that you have the convolution of two signals, then their Fourier transform is the multiplication of the Fourier transform. So here we have H convolute with X, then you do Fourier transform, then the corresponding Fourier transform will be big H times big X. And why is this very interesting? Well, you see that now we can connect everything together. You see that this H convolute with X from what we talked about in chapter 2. This can be viewed as what happens when you apply a LTI system to your input signal X, right? So H is your impulse response. This small h is your impulse response. And when you convolute it with your input signal X of t, then your Y of t will be the output response, output signal of your LTI system, right? You have LTI system characterized by this small h, and when you input X, you output Y, which is equal to a convolution here. And so then this relationship tells you that you can find the Fourier transform of your output signal very easily by just doing multiplication of the Fourier transform of your input signal and the Fourier transform of your system function, which you write as big H. And okay. And now you think this might be a bad notation because we also had something called big H before in chapter 3, right? In chapter 3, we call the eigenvalue of your LTI system as big H. We say for every LTI system, the e to the j omega t is the eigenfunction of your LTI system. Actually, we say e to st, but we focus on the purely imaginary case here. So we say that those exponentials are the eigenfunction of your LTI system, and those are the corresponding eigenvalues. We call them h of s, or for s equal to j omega, it's h of j omega. So we have h of j omega here, and we also have another h of j omega here. So it looks like we are using bad notation, but it's actually good notation because those two big h are actually the same thing. Okay. So this is something we can talk earlier, but we choose to talk it here. That is, the big H defined here is actually the Fourier transform of the small h, because we need to remember something. So in chapter 3, we have this equation of how you calculate big H from small h. Right? So that's not, you can flip back to the notes, but this is the correct formula. We have h of s is the integral of minus infinity to infinity, h of tau e to the minus s tau d tau. This is what we derive. This is something we derive about how you calculate big H from small h. And obviously, if you put s equal to j omega, then you have j omega here, j omega here. And now you can compare this to our favorite equation, favorite Fourier transform equation, or inverse Fourier transform equation. And it's not here, but you remember that for the Fourier transform pair equation, the inverse relation, we have the big X of j omega equal to integral minus infinity to infinity, small x of t e to the minus j omega t dt. So you see that big H of j omega is actually the Fourier transform of small h. Okay. And so we know two things here. So because small h and big H satisfy this relationship, so obviously they are a Fourier transform pair. So Big H is a Fourier transform. Big H of J omega is a Fourier transform of small h. And so this also solve another question we did answer in chapter 3. That is, we have this equation. This equation tells you how you calculate big H from small h. And we didn't know how you calculate small h from big H. But now we know, because we know you want to inverse this relationship, then you do the synthesis equation of the Fourier transform, right? This is the analysis relationship. And you can do a synthesis equation, and so small h is just, okay. So small h is going to be integral, similar integral, so 1/2 pi integral minus infinity to infinity big H and e to the j omega t dt. Yeah. So this is not quite totally related to convolution. This is not something derived from convolution property, but we decided to talk about it here. And this is very important thing. So yeah, the system this impulse response small h is a Fourier transform is the system function big H, which we defined before as the eigenvalue of the input signal e to the j omega t. Any question about the any question about the relationship between small h and big H? And okay, this is very important thing. We are going to use this, and yeah, we are going to use this throughout the whole class, and it's very nice to know. And once again, so now we know this small h and big H has this Fourier transform pair property, and we also have this convolution property. We can view this calculating output signal as a convolution on small h and small x, and we can do an easier calculation, go to the frequency domain, which means that we Fourier transform everything. And here we see that the big Y is just big H times big X. So yeah, it's a very nice property if you view this as systems. And also something we already see, but not quite. Okay, it's a little tricky. So one thing interesting here is that you see this h of t and x of t are kind of symmetric mathematically. X of t is some function, and h of t some function, and big H of omega is some function, and big X of omega is some function. You see they are kind of interchangeable. So it's interesting that you have symmetry here, but what I want to say is you still need to be careful, because sometimes you still need to interpret X as input signal and H as your system function, as your impulse response, and yeah, don't mix them up too much, even though mathematically they are the same. Okay, so let's go back to the convolution. So, well, the most important thing is you remember this convolution Fourier transform is a multiplication. We can also go through the proof of this. So the proof is not too hard. You basically write down the integral and changing the order of integral. So the proof is not too enlightening, but we can still go through it. So y over t, yeah, basically proof of the calculation. So y of t is the convolution of h of t and x of t. And you just write down the convolution here. So h of t, then minus tau and x tau integrating over. And let's see what we do. Okay, so we do a Fourier transform on this thing. So this is some function of t, then you do Fourier transform. So integrating over everything with t and multiply with e to the minus j omega t. Okay. So we just apply the analysis relationship, analysis equation of the Fourier transform. Then, as we said, so this is what you usually do. You change the order of integration. So you have d tau first, then dt. Then now we want to do dt first, then d tau. So now we look through everything what depends on t. This h of t minus tau depends on t, and this e to the minus j omega t depends on t. So they are inside, and the h of tau doesn't depend on t, so they are outside. Now we do this integration and do some change of variable because we want h of t instead of h of t minus tau. So we change t minus tau to t. Then the boundary doesn't change, and dt and dt minus tau is the same. But I get the h e to the minus j omega tau from here. And if you do a change, and then you look at this integral h of t to the minus j omega t dt, and they realize that is this equation shape, this equation, and that's just h of j omega. Okay, so we got h of j omega here, but h of j omega doesn't depend on tau, so you can put it outside the integral, and then you look at this integral, you realize that's big X. So, yeah, so that's the derivation. Big Y equal to big H times big X. Any question? No. Okay, nice. And a little more interpretation. Oh, I guess we can also see it here. So from here, we can also just rederive the property about the convolution, right? So remember before we said convolution is like the multiplication. So you have the commutative rule and associative rule, distributive rule, and you can easily see from here because you do Fourier transform here and here. The big H and the big X, the multiplication is just usual multiplication. So it has all the three multiplication rules. You transform back, you can get all three rules. Okay, and we can also view this in block diagram. So before we write those block diagram with small h, and now we can write them in big H as the frequency response. So the response in frequency domain. And now like I said, we can see the commutative relationship again. So if we review them in frequency domain, then apply big H and then apply big H1, then apply big H2, is same as apply big H1 times big H2. Because before we will have small h1 convolute with small h2, and if we go to frequency domain, then that's big h1 times big h2, and this multiplication just commute with each other, so you can change the order and separate them. So the same as apply big h2 first, then apply big h1. Any question? Should not have too much question. Yeah. And okay, and something it should not really be under the convolution discussion. Okay, so this is a discussion about the relationship between small h and big H. Okay. So we say that now from now on we are always going to switch our perspective back forth between the time domain and the frequency domain. So sometimes we view a system with small h, sometimes we view a system with big H. And there's some trouble in doing this sometimes. That is, sometimes you have a small h, but you don't have a big H. Because if your system, so if this small h is bad enough, then remember there might be issue in the convergence of your Fourier transform. So sometimes you have small h, but your big H just doesn't converge, then you cannot write a system with big H. But if your system is stable, then remember so this is something we tested a lot in our first midterm. So the stable condition of your TI system in terms of your small h is that the absolute value of your small h integrating over is some finite value. Okay. Now this thing, now you compare this to our convergence, our Dirichlet property, which is convergence conditions for some signal. Dirichlet properties are sufficient condition for a signal to have a convergent Fourier transform. Okay, and so this is the first dirichlet property, and you also have the other two property. That is finite value of maximum and minimum and finite value of discontinuity. So anyway, if all three conditions are satisfied, then your small h will have a corresponding big H because of the dirichlet properties. And usually you have a system, then if your system is not too weird, then your small h will satisfy the other two property. So for multiple physical systems, the other two property will be satisfied. So the bottom line is your small ht is stable, then very likely you will have a big H of t. You do the Fourier transform, then this big H will converge. Okay. So yeah, so this is all this I want to say. Any question? Because of the dirichlet condition. Okay. So I guess let's go to some example. This is quite fun. So we can see lots of things back and forth. So first there are very easy LTI systems. So the LTI system of H being delta of t minus t naught, which you should remember what this do is applying a time shift on your signal. So your input is x of t, then your output y of t is going to be this x of t minus t0, because you do the convolution integral, and this delta function will pick up this t minus t0 here. Okay, so this is what we know, and then we want to check this again by going through a longer route. So we want to go to frequency domain and do multiplication, then transform back and check it out. We get the same result. So this is what we do. So h of t is this delta here. Then we can calculate the big H of j omega. So for the transform of this thing, you can do the integral, and we already do the integral somewhere, I believe, and it will give you e to the minus j omega t naught. Okay. You can just look at it here. Then we can have big Y equal to big H times big S of j omega. This is what we've been talking about. So in the frequency domain, your LTI system, just multiply your x of j omega with your big H. Okay. So that's big X of j omega and times this thing. And then you Fourier transform back, then this is one of the property we've talked about in Fourier transform, right? So we have a time shift, then its Fourier transform is you get this extra e to the minus j omega t naught. Let's see if we can find this very replaced. Time shift, it's quite, it should be before this. Time shift, time shift. Yeah, here. Okay, so t minus t naught, you will get the extra e to the minus j omega t naught. Okay, so everything check out. You can derive this easy relationship by going to the time frequency domain and multiply your signal with system function. Now I need to go back. Okay, so you can calculate this. Yeah. So that's nice. You check out, and we have another example. So y of t equal to dx dt. Once again, this differentiation is an LTI system. And well, now we go to frequency domain. So we do Fourier transform on both sides, and y just become big Y. Then dx dt. We have derived this, so you do Fourier transform of dx dt, you get extra j omega, then you have big S of j omega. Now you look at this equation and you want to view it as a LTI system. So you should have big Y equal to big H times big X. And so this extra j omega should just be a big H. Okay. So yeah, so here we derive the system response of this LTI system obeying differentiation. Question? And okay, and we also learned something here, right? You remember the small h of this system is our unit doublet. So now you know the Fourier transform of your unit doublet is this j omega. There. I guess you don't want to think about that too much because they are very divergent. Yeah. But you have the system response here. And quadrant? No. Okay. Let's look at other example. Lots of example because it is really fun. Okay. So ideal low pass filter. So we talk about this in some. We talk about this a little bit in chapter 3, and we're going to talk about them more because now we have we have more understanding in those big H. So remember, a filter is something that select out some range of frequency. So it's basically a block signal in your frequency domain. So big H and low pass signal, you want to pick out low frequency part of your signal. So it's 1 when your frequency is less than some cutoff omega c, and it's 0 outside of the cutoff. Okay, and it's just a reminder. So this minus omega c to omega c is called passband, and because it's the value 1, so those frequency will just pass through, and it's called stop band outside. Okay, anyway, mathematically this is just a square wave signal, and we know the reverse Fourier transform of this thing. We've seen this quite a few times. You have a square wave here, then the corresponding Fourier transform will be the sinc function. And so that's not repeated the calculation here. And as behavior normalization, things are all correct. If you do inverse Fourier transform, the small ht will be sin omega ct divided by pi t. Yeah. And okay, so that's the impulse response. If you want to get this, so that's the impulse response in time domain. If you want this kind of frequency response, and once again you plot sinc, you look like this. So it's up down, and center around the 0. And so that's a little troublesome because this impulse response first is not causal because it has this negative part. Okay? So that's quite annoying if you want to design a system that, if you want to design although there can be system that's not causal, but if you want your system to react in real time, then it should probably be causal. And also is you can see it has lots of wriggle here, up down, and this wriggling behavior is kind of hard to design. So we control this thing, or we approximate something. So we still want to control a low pass filter. So we want to approximate it with something that's causal and not oscillating. So we do something very coarse. So we basically just cut off this thing with it's not even exponential, it's a polynomial decay. But anyway, we approximate this with the exponential decay. Okay, yeah. So that's what we do. We say looks like something decay, so we just do an exponential decay here instead. Okay? So that's our approximate filter. So this h of t just the exponential decay, and we want it to be causal, so we cut off at t equals 0. So unit step function times the exponential decay. And we also see this signal quite a bit of time. Well, we were viewing them as signal. Now we view them with impulse response, and we know it's Fourier transform. Yeah. So the Fourier transform of this HT is the system response, also called frequency response, 1/j omega plus 1. Okay. And let's have a picture here. So small h of t is this exponential decay, and its decaying time is like 1. And h of j omega is a complex function, so it's a little hard to plot in a 2D picture, but we can plot its absolute value, and its absolute value will look like this. So you can see it's quite far away from a block signal, but at least it's kind of centered around 0. It's higher in a 0 and decaying out on the outer part. Any question? Oh, yeah, please. Yeah, you can speak in Chinese. 不是抠手就不好盖你的系统啊，就是你想象如果你是 real time 的系统的话，你的 signal 进来，那不是抠手系统，你就必须预测未来发生什么事，才可以有这个 response 嘛。因为抠手系统就是只看发生过的事情，对吧？那不是抠手系统，你就没有办法 real time 做，因为你不知道未来会发生什么事嘛。Okay, no question. No other question. Then let's look at the other example. Okay, this example is a bit more tricky in terms of calculation. Yeah. And I think we see this in something similar to this in midterm, right? So we have our small x of t and small h of t. They look kind of similar. So you have exponential decay cutoff and another exponential decay cutoff, and in interval 2 we will just brute force this with convolution, and this is actually not too bad because you are cutting off at the same point, so it's think about this quickly. I think there are still 2 parts, but anyway, you have exponential decay cutoff and you have some parts on it. And you can do the convolution. You can do the convolution integral, and you will get your output. But here we want to do something smarter. We want to do this without integral. So we go to frequency domain, and well, the Fourier transform of this thing we already calculate. That's why we can skip the integration because we know we have an exponential decay cutoff. Then the Fourier transform is going to be this 1 over b plus j omega and 1 over a plus j omega. Okay. And we go to frequency domain. So our output y is small h convolute with small x, and our big Y will be, we didn't write it here, but big Y should be big X times big H, and so it's just this thing. Right? Okay, just those two multiplying together. Then we use this a trick here. The trick should really be told a little more, but we had this hiding teaching the trick inside our example here. But anyway, the trick is that we want to do the inverse Fourier transform of this thing, but we haven't seen anything looking like this. And obviously you can do the integration, but integration is also pretty hard, okay? Because we don't do that much about complex analysis. But one thing you can do is you just breaking this thing into things we know. So we know how to calculate the inverse Fourier transform of 1 over a plus omega, because it's just a pair with this exponential decay. So we break this thing into 1 over a positive omega and 1 over b positive omega, and both multiplied by some constant a and b. And you can just solve for this a and b, but you can multiply these together and compare to this thing. So here you see that big A times small b should equal to big A times small b plus small a plus times big B should be equal to 1, and big A times omega plus big B times omega should equal to 0 because there is no omega term here. So A equal to minus B, and then you solve a little more, you see that A equal to B minus A and B equal to A minus B. Okay. So you can get this y over omega equal to 1 over b minus a, and this 1 over a positive omega minus 1 over b positive omega. And now you don't need to do any integral anymore because you know the Fourier transform pair. This look like this, and this look like this, and this look like this. And so the inverse Fourier transform of this thing will just be 1 over b minus a, and the exponential minus at and the exponential minus bt. And let's have an extra slide about this trick here, which is called partial fraction expansion. And it's a really nice trick. And well, the idea is just you have something look like this, then you solve for a fraction form like so you have a rational function like this, which is a polynomial over another polynomial. Then you can always solve for a fraction form like this. It's a over a positive omega plus b over b positive omega. And if you want to write this in more general form, then you have some f of x, which is a polynomial divided by another polynomial, but we already written it as roots. So a polynomial over x plus a or x plus b plus x plus c Then you can always write this as this partial fraction expansion, which is a over x plus a, b over x plus b, and c over plus c. And I skipped something here, so this polynomial x should have lower degree than the denominator polynomial. Otherwise, you just get another polynomial term. You can do the division first, right? Division is a reminder. So if you have higher degree on the upper side, you just get an extra polynomial here. And you are probably not going to see that. But anyway, so you have this fraction expansion, and those ABC are just constant. And you write down this equation, then you need to decide what those ABC are. Obviously, ABC depend on the polynomial here. And I think there are more systemized way to solve this, and you can probably look at it online. But for the purpose of this course, we are always doing this for pretty small pretty small equation. And you can just do the brute force. You can just do the brute force solution. Just multiply everything here and compare the terms here and compare the terms here and solve for your ABC. That's what we did here. Yeah. So that's partial fraction expansion. Any question so far? No? Okay. So anyway, this is a very useful trick, and you are going to use this a bunch of times throughout the course, because this is so for spoiler, this is how you solve differential equation. Anyway, so let's back to this example. It's actually not finished. So we have y of t equal to this 1 over b minus a e to the minus atu minus e to the minus bt times u of t. And this is not finished because if a equal to b, then you have 0 divided by 0. actually undefined, and it's annoying. So we need to be careful about this and deal with A equal to B with special case. Okay. And yeah, so A equal to B, you cannot do the partial fraction expansion. So I guess I should be a little careful here. So this ABC here should actually be different number. So what happens if you have the same number here? So we need more trick here. So if A equal to B, then Y just equals to 1 over A plus omega square, single term. And you can get this once again from our A plus omega. This is something we know by just doing a differentiation on it. Right? Because yeah, 1 over x, you do differentiation, you get 1 over x squared times some constant. Yeah, constant here is j. Okay. Well, constant is a little complicated, but anyway, so this is correct here. Yeah. So we can get this square here by viewing it as the differentiation of omega on our favorite function of 1 over A plus omega. And then once again we can do the Fourier transform parity. So we know once again we know our 1 over j omega, A plus j omega is the Fourier transform of our exponential minus at as u of t. And then we do a differentiation on this side, and from the property we had before, we'll see that we just get HRT here. Let's see. Our differential property, I'm a little confused. Our differentiation property is, let's see, 2RT here. Okay. Yeah. Oh, okay. I remember. Yeah. So let's just look at this here. So you do differentiation on x, then you get h bar j omega on your frequency domain, and if you do differentiation on omega, then you get h bar minus jt here. Okay. So okay, the h bar minus jt here, and your minus j cancel you with your j, so you just get the h bar t here. Okay. So that's the H04 solution. Any question? Okay. That's very interesting. That's how you, yeah. Okay. Then let's look at more example. Once again, we do convolution without doing convolution. Now this is something you can you can still do, but it's much harder to do with convolution. So once again, you have x of t. Now it's a sinc, and h of t is another sinc function. And we want to calculate the y of t. Then you can do the convolution theoretically, but you see the convolution of two sinc functions is going to be very ugly. But if you go to the frequency domain, then the frequency domain are just two block signals, right? So yeah, two of those block signals, and it just one omega less than omega I, or omega 1 when omega less than omega c. And you multiply those things together, then it's just going to be another block signal. And the threshold become the minimal of those two, because you need both of those satisfy to be 1. And 1 times 0 is 0, and 1 times 1 is 1. Okay? So your y of j omega, big Y of j omega is going to be another block signal. And you can Fourier transform this back. And obviously, your block signal is going to transform back to another sinc function. So your y is just a sinc function, and the frequency is going to be the smaller frequency of those two. Question? So yeah, this is a very nice property. You can go back and forth between frequency domain and time domain. And we still have time, so let's go. Okay. If there is no question, then let's go to this multiplication property a little bit. So this is the dual of the convolution property, and it looks very similar but a little different because of our normalization. So the property says that if you have your signal is a product of two signals, then the Fourier transform of this R is going to be kind of like the convolution of the two Fourier transform, but it's a bit different because our normalization, so we get the extra 1 over 2 pi here, and also because of how we write our Fourier transform, so you get a J everywhere. Okay. So, but if you look at this not too carefully, then you see the multiplications Fourier transform is going to be the convolution of the Fourier transform. Okay. The Fourier transform multiplication is going to be the convolution of Fourier transform. Okay. So yeah, as we said, we have that those two equations looks very similar, and we have duality in basically every property. So this is a dual of the convolution property. And this property is interesting because, this now go to more actual signal processing, because sometimes we will do this multiplication of the other signal as a very useful way of signal processing. We use this multiplication of signal to what did I say? This multiplication of signal is sometimes called amplitude modulation. So maybe let's look at the picture here. Although this picture is, I should not look it into too much detail. It's a little weird. But anyway, the high level idea is that, so this is something we do in radio. We have a high frequency carrier signal, look at this, and it's some sinusoidal signal. And there is some matrix signal which has lower frequency. And the way to send our message signal is we multiply it with our carrier signal. And then this is called AM signal, amplitude modulation. And then the resulting signal will look kind of like this. So you have your higher frequency carrier signal inside, and your your message signal will modulate this output signal. So you will have the outer envelope look like your message signal. Okay? And this is a way to send your signal through frequencies. Okay. And this is nice because you can shift your signal to a different frequency band, and that's why you can actually have many radio channels, because you can change your carrier signal frequency, then that will correspond to a different frequency band. And that's just about time, so let's stop here. Any question? Otherwise, let's have a 10-minute break.
期中直接看那个，然后那个期中我们再玩一周，
因为怎样？
前3天才交作业，他觉得有点赶。
前3天才交作业有点赶吗？我可以想一下。好，看看有没有笔。期中，所以你还是不行。可是你不是那个吗？所以我是2个都要签吗？
对。你
这样子，我记得你那时候跟我讨论过，我应该要离2个人也好了，不要讨论这些。对。要不要？没有，我可以签啊，只是你这样子会不会有修的问题？我是觉得你那时候
如果这2个要成绩，
讨论就要
右边
要不要修这一套？
他那边说的意思是，先不讲这边，就是这2项成绩。他的那个为了传送就是打，
因为我好像还可以啊。
对，然后他这边
可是有放的。
那你这边传出来的传送，对，是这2个传送的那个，就是不够好的选，所以他们不是。
但是你这样子没有理就没有理了。
对，就是刚刚好。
你说放在后面。
但是你这样子选，
你不管丢它放在
因为你那时候好像说你想，你是什么理由来说是想要修的？就是之后自己要学这些学号。
你说的很多就是说他在要看你谁成啊，
对，那你有没有听懂一些？对。
这大概有知道，但是我现在还
好，
是那，但是老师我了解这里的那个对流性质，但我在想说，它这个居零，它这个零是怎么带进去的？
居零，这一题是要写居有零吗？不是就是把数字丢进去吗？
哦，但我在想说，就是它这个零要，就是它是怎么变进去？就是我在想，因为我就是我就是
应该来从你这里找好了。
在上
就
面。
是把 Fourier 全是风公式，就在这里嘛。这个，没有，这里是丢在这里的，这里应该是对，应该是这个，确认一下。现在要算小 G 吗？
对，
对，所以是这个公式，然后把它替代零。对啊，那就是这里的 T 变零。对，就是你可能想错公式了。对。
相加的话，它会这样。所以你可以想，就是像那个来做那个什么，对，就是那种它只会真的，然后它的 apple 东西从单只那个从那个这个这个，
看你就是这种画的那种就像上面画那个，上面有个画，
我知道，那你说我这个想法，你选择的那个比较安全，对啊，因为你说上面就是一个频率下来，然后频率就是你那个频率有不同的安全，对，然后它转它那个多长就是它的对到，然后它转多快就对到它，然后你相加就是你的那个。负相加就是你就把它加在后面，然后它就加到负数相加。那你不是不同频率乘上它的自己的各自有各自的安分乘完之后全部加在一起，然后它多长就是它的安分多长，然后之后大家加在一起就是头尾要相连这样，它就开始这个是的，对，然后大家都自己自己。
对，这张图那个画出来，
因为刚好复数是负面的时候比较
你这样看就会有我懂这个比较热不会，
只要看学校比较好的时候。
OK， 期中考这个
还要延长
可以吗？是不是？勉强还可以吗？
我是不觉得还好，但是老师看你进度，因为你往后演就会影响到期末考，那老师后面
虽然说期末考还是聚焦下去，但是先试看好了，因为期中考的章节比较少，对，
就维持嘛。
对啊，我维持好了，勉强对啊。 我们试试看。期中考就维持13号，虽然说作业这样比较轻一点，但是期中考我们可以久一点。13号，对吧？
还是下礼拜交作业？
对啊，下礼拜然后下礼拜都有作业。
那下礼拜就是第4课以下。
对。之后我们可以有一半的作业。Okay. So back to our multiplication property. So that's something we can do. We can multiply our signal with another signal. And so something confusing is that, so you can kind of think this as a system. So your input signal and you provide another signal get the output signal, but something that might or might not confuse you is that if you think this is a system, then this system is not IOTI. Okay? Because this is not something time invariant. Think about it. So that's something you might want to remember. But anyway, let's then look at how we play around the modulation a little bit. So what happens if you do a modulation on your signal? So this example, we have our modulation on this kind of system. So your input is some SOT, which is something general, and we think this SOT, well, we don't actually know what the SOT is, but we get big SO j omega here, and want to analyze this on frequency domain. So from some input signal SOT, then we have some I guess carrier wave. P of t is just this cosine wave, cosine of omega t. Okay? Then we want to see what happened to this signal on the frequency domain. Okay? So yeah, we want to use this formula where you do multiplication on time domain, you get this almost convolution on frequency domain. So let's first change our P of t into frequency domain, and cosine omega t, well, it's once again it's the exponential omega t minus plus exponential plus omega t, and yeah, and those two exponential, you think about it in terms of Fourier transform, there are two delta functions. So you get pi delta of omega minus omega pi delta of omega plus omega here. So two specs, two delta function. And yeah, I've seen this quite a few times. But anyway, so small p cosine omega t and Fourier transform get two specs. And delta functions are particularly easy to integral. So now we can easily write down what are the big R, what are the system output. Well, I guess it's if you view this as a system. So what is big R in the frequency domain is your big S and convolute with your big P. And when you convolute with delta function, you just get a shift in your signal. Here is a frequency shift, and yeah, so you get frequency shift forward and frequency shift backward. So you get these two things, and their height is going to be 1/2, 1/2. Okay, so you kind of split your signal into two signals shifted in frequency. Okay. And yeah, so once again, this is kind of explain our modulation, why this works. So the idea is that there are many radio signals you want to send. Right? There are many different radio channels and they all want to send some message. And well, the message is going to be your voice message, so they are all in similar frequencies on low frequency thing. But but there are many different video channels, and how to make them not overlapping with each other. Because if everyone sends signals around here, then they are going to be all overlapping, and you are not going to be able to discern all the signals. So the way how you do this is then you do this kind of modulation. So you multiply your signal with this cosine omega t, and everyone has different omega naught here. So you can so video channel 1 can push their signal to this plus omega naught, and video channel 2 can choose maybe even higher omega naught, then push their signal to something around here, some big omega, something around this omega 1 or omega 2. Yeah. Then video channel 3 can push their signal to some omega 3, and then everything will be separated on this frequency domain, and then you can have your separate video channels. Okay, so that's the idea, and so that's nice. But you might ask, now you push your signal to all those different video frequency bands, but how do you decode your signal back to get back your signal in actually this low frequency thing? Because you want to hear your radio voices in normal human frequencies, not something very high frequency. So it's actually very easy. So you can just do the same modulation again. You just multiply your P of t again. Okay? So what happened? So we have your R of t from your signal times your P of t, which is just cosine omega t. And if you multiply your R of t with your cosine omega t just again, then we can do a similar calculation, and we once again go to frequency domain, and P of t, you know, its frequency domain are those two spikes. And now I think about this R of t, and get time shifted by those two spikes P of t. Then you get shift left, shift right. Then this shift to here, and this shift to 2 omega naught. And also a shift left, so this peak gets shift back here, and this should get shift to minus 2 omega naught. So in the end you get this signal. So something in the middle, something gets shifted back to the middle, and something at 2 omega naught and something at minus 2 omega naught. And you can just filter out your really high frequency domains, frequency signals, then you get back your original signal at your original radio frequency. Any question? So that's this is a very primitive idea of how you do AM modulation, although obviously there are many details we left out. Okay. You can see this is quite interesting. And shift the frequency around. And okay, let's get another not so much about application example. So this is another example how you do the multiplication property of Fourier transform. And your x of t is sine t over 2 over pi t squared. And you can just view this as the multiplication of two sinc functions, so sine t over t and another sine t over 2 over t over 2. And sorry, we actually do sine over t, sine t over 2 over t. Okay? And you want to make the Anyway, yeah, and put pi here, and supplement another pi. Anyway, so you have two sinc function, and we know the Fourier transform of sinc function is going to be the Fourier transform of sinc function is a square root function. So the Fourier transform of your x is going to be the convolution of two square root functions. So the Fourier transform thing is going to be two square root function. And you think about the Fourier transform. You think about the convolution of two square root function, it's going to be looking like this, because those slope correspond to when your square root function has partial overlap. Too lazy to draw the picture here, but you think about how you do the convolution back in chapter 1. You're going to see the overlap between two signals, and yeah, so that's when they have partial overlap, and this is when they have full overlap and partial overlap, then no overlap. Okay. And yeah, there is not so much interpretation here, just nice mathematical example. Any question? Okay. Yeah, then we can also do this frequency shifting thing with kind of application. Okay. So the idea here is we want to construct frequency selective bandpass filter. That means we want a filter that pick out some frequency. So maybe we want to pick out a frequency around here, something like that. Okay. And you can control that with the LTI system, but the issue is that it's going to be not so easy. So you want to select different frequencies. You kind of want to this be a little tunable. So you want to select, filter out maybe the same band width around different center frequency. And if you want to change the center frequency, then you need to change a lot of different parameters your LTI system. And if you want to think about this in actual engineering, then that means you need to change a lot of parameters, your resistors, amplifier, capacitor, etc. And it's going to be very annoying. So, but we can do something else instead. So what we do is we can shift the frequency around, and so we have a filter already at some fixed frequency. Then we can just shift the frequency of our input signal around, and that will be equivalent to shifting the center frequency of your filter around. So let's see this in more picture and details. So maybe a schematic is this. So you have input signal, then you can multiply, you can do this multiplication with e to the j omega ct, which will actually just shift your frequency of your input signal and get some y of t. Then you can do your filter, and it will filter out some frequency band of your y of t. Then you apply a reverse frequency shift, and you get some output f of t. And let's look at this first. It's very intuitive. So you have a signal in frequency domain, look at this. Then first you do frequency shift to left or right, depends on what you want to do. So we have shifted right here. So we add everything with some frequency. Then you apply your your filter. So maybe you have a low pass filter here. So you will filter out this part of your signal. So we are here right now. Then you shift your frequency back here. So the final output signal here, ft is this part. And so this three-step operation is equivalent to you just filter. You have a filter on this part of your signal. Okay. So that's a very nice trick to to change the center frequency of your signal. And one thing you should probably remember is that now those two operations are not LTI. Okay. So you might ask why are we getting this magic? Why don't we just build a LTI filter that do this whole thing? Why we think this is hard? We are bypassing a hard part because we are using two non-LTI system. Okay? So yeah, this is not LTI and this is not LTI. And yeah, so you should not. So yeah, this is not LTI, and so there is. Yeah, so you should not really think this with small h and big H. This is just some frequency shift operation and a frequency shift operation here. Okay? So hopefully that don't confuse you too much. And anyway, so let's back to a little more theoretical about this thing. So we claim that this is going to be a frequency shift and this is going to be a frequency shift. And that's really kind of obvious, but let's do the calculation once again. So think about, so if this system has input xt and output y of t equal to exponential e to j omega c t. Is it correct? Okay. Hopefully this is correct. Yeah. So y of t is e to j omega c t x of t. And then want to say it was big Y of t. So you can do this in two ways. The first is you just look back to your one of the property we have derived. That is, did we derive it? We probably didn't, but it's quite easy to derive. You can derive this property. That's you have a frequency shift in your Fourier transform, then you get HR e to j omega t in our original signal. So you compare these two and this thing and this thing. So you see that you should have big X of j omega minus omega c here. Okay? And but we can also use our multiplication property that we just taught. So we will have y equal to 1 over 2 pi, the convolution of Fourier transform of e to j omega ct and the Fourier transform of x. So Fourier transform of x is just going to be big X of j omega. And Fourier transform of e to j omega ct is going to be this delta function. And times 2 pi, so that cancel out with the 2 pi of in our equation. Once again, 2 pi here. Okay. So this is a harder calculation, but you can get this integration and this delta function pick theta equal to omega c. So yeah, you get the same result. So please check out. So yeah, this multiplication with e to j omega c do what we think it should do is shift the frequency. I think it's forward. Yeah, it's kind of easy to see because every e to the omega become omega plus omega c. Okay. And yeah, then the other operation you do is you times e to the minus j omega c. You just change omega c to minus omega c, and that will shift your frequency back. Okay. So yeah. So everything together, you will do this thing. So you can shift your filter around center frequency being 0 around to everywhere by doing two frequency shifts before and after. Any question? No. Yeah. This is quite nice. And now we have a small summary here. So since we'll talk about, so it should be, I think, this should probably be included in your test. But also nice to memorize some of them. Let's go through it quickly. So linearity, obviously we have linearity, and you have the time shift on your time domain. You get extra e to the j omega t naught in your frequency domain, and duality of this property. You get a frequency shift, then you get extra plus j omega naught t in your time domain. And conjugation, you conjugate your signal, then you get conjugate and the negation of frequency in your frequency domain. And if time reversal, you just get frequency reversal. And as a special case of scaling of your signal with some A. And scaling your time with some A. Then you get 1/A and scaling of your frequency with 1/A, 1/A absolute value of A. And then the two property we just talked about. So you have convolution on time domain, that becomes a multiplication on frequency domain. And if you have multiplication on time domain, that's a convolution on frequency domain, also divided by 2π. Okay. And you get differentiation on time domain, you get h bar j omega on frequency domain. And the integration, you get 1/j omega, but also have this weird pi big X of 0 delta of omega term that we don't quite derive, you just need to remember. And the duality of this thing, so you get a differentiation on frequency domain, you get the HRT in your. We have weird normalization, but you get J d omega in your frequency domain, and you get a Tx of T in your time domain. If you want to more symmetric, then you divide the J here, so you get minus JT and a dd omega. Okay. And okay. There are a whole bunch of symmetries about reals. So x of t is real. Then from the conjugation property, we have x of j omega equal to x star of minus j omega. Then you can get a whole bunch of properties. So the real part of your Fourier transform domain will be even, and the imaginary part will be odd. And also the amplitude will be even, and the angle will be odd. Then also there are a whole bunch of properties if you think about even odd. So thing is, if x of t is even, then big X of omega is going to be even, and x of t is odd, then big X of omega is going to be odd. Then you combine with the real or imaginary thing, you get a whole bunch of property. And also because of this thing, you have an even odd decomposition. So the even part, so if your x is real, then because of this real part being even, the imaginary part being odd, so the even part of x will correspond to the real part of the Fourier transform, and the odd part of x will correspond to the imaginary part of the Fourier transform. And we have possible relationship, which is energy in x domain equal to energy in frequency domain divided by 2π. Okay. Question? No. Okay. And how do we? Yeah, we should be on time. And once again, we have. Wait, why do we? Oh, okay. I should have. Okay. We are missing our synthesis and analysis relationship. Should put them somewhere. But anyway, yeah. But okay, so this is some reminder about so. Okay, so this is actually a reminder for chapter 3. This is for the Fourier series expansion for periodic signal. Anyway, so we have some basic Fourier transform pairs that are nice to memorize too. So first, signals. That's why we have those two equations here. So if a signal is periodic that can be written as this Fourier series ak times e to the, oh, it's really small. Let's have where is this? Okay, so the signal is this ak times e to the jk omega naught t, which is a periodic signal returning in terms of the Fourier series. Then when you do Fourier transform, then you get this, which is whole summation of delta functions. Okay? So each e to the jk omega becomes 2 pi delta omega minus k omega naught. Okay? So this is the linear combination of the property just down here. So e to the j omega t going to get transformed to a delta function with omega minus omega naught and hr 2 pi. And if you have a summation of a whole bunch of e to the j omega naught t, then you get a summation of a whole bunch of delta function. And yeah, we spent the whole section talking about this. And there is Fourier series coefficient, but it's not too interesting, so ak. Let's skip those. And yeah, and there is sine and cosine, so cosine can be written as two exponential adding each other, so you get two delta function adding each other. And sine is the difference of two complex exponential, so you get difference of two delta function. And also kind of special case of this thing. So omega naught equal to 0, then your x of t is a constant. Then you get a delta function here, 2 pi delta of omega. And okay, oh, it's still small. Okay, it's still looming. And we have our, okay, this is very annoying. Periodic square wave. I think we don't quite talk about this, except that why does this look weird? Wait, let me try. Hold on. Oh, okay. This is weird because it actually has a line cut off here. Let's look at this. Okay, so this is the third column. Okay. So our square wave was somehow also periodic. Then I think we only talk about this at the very beginning, where we try to derive Fourier transform from Fourier series. Yeah. But anyway, so you have a lot of square wave, then you will have these samples on your sinc function. Okay? So we have sine k omega over k, which will look like k omega naught. So the sinc function then sampled by these delta functions. Anyway, yeah, and also then the more interesting thing, it's something with more application is this impulse train. So if you have those equally spaced out delta function as your input signal, which is also periodic, then you do Fourier transform, you also get something looks similar. You also get, so you have an impulse train here, then Fourier transform is also an impulse train. So also something is that's equally spaced out delta function. But if the spacing here is larger, then the spacing here is smaller. You can see you have t here, so if the spacing is t here, then the spacing is 2 pi over t here. And also 2 pi over t, the amplitude also get changed. So those are weird periodic signals, and then we have more convergent pairs. Then I have square wave signal and the sinc go to square wave signal. Talk about a lot of them. And then we have delta function transform to constant function. That's just a reverse of this thing. Okay. And we have this unit step function transform to this where 1 over j omega plus pi delta over omega. Okay. You kind of need to remember this. And once again, delta function transform to e to the minus j omega naught t naught. That's the reverse of this thing. And then something we talked just today, kind of. So this e to the minus at, so this exponential decay transform to 1 over plus 1 over a plus j omega. So this is the first few examples we have. And then it's actually quite important because going to see very soon that they are useful in solving differential equation. And then we also want the powers of 1 over a plus j omega, and we derive those by doing a differentiation on this side, and then you will get a corresponding t on this side, and if you do differentiation more times, then you get some polynomial on t, actually some powers on t. So t to the -1 divided by the -1 factorial here. And want this to converge, so you want the real part of a to be bigger than 0. So, question about those reviews. I think basically all of this, I think except this one. Okay. I think one time. We will probably just finish chapter 4 today and stop. And yeah, so that's part of this thing. So it looks that is use the Fourier transform to solve our linear constant coefficient differential equation. Okay. So remember from it's quite a long time ago. It should be on chapter 2, I think. Anyway, so we talked about those linear constant coefficient differential equation, but we didn't give you a way to solve them. Now I'm going to tell you how to solve them. And reminder again, so those are linear equation. We call those differential equations linear because they are linear in x and y. So we only have linear x, linear y. Then have y squared and x squared. And constant coefficient because the coefficient ak and bk here are constant. They don't depend on t. And yeah, linear constant coefficient. And obviously differential equation because you have whole bunch of differential here, and also it should be called nth order because you have some big N here. So we see a little bit of this. Okay, and okay, so there are a whole bunch of things here. Should I put here? So first is that this can be viewed as a LTI system, actually also LTI system, if we have the initial race condition. Okay, so here we basically just implicitly assume that we have initial race condition. So we want to solve this equation with initial race condition, and that's a LTI system. And the LTI system we want to solve for the small h or big H. Okay, and we kind of do this a little bit in chapter 3, as we can get the big H of the system by subbing x of t be equal to e to the j omega t. Then because we know e to the j omega t is the eigenfunction of your LTI system, then you will get a corresponding eigenvalue here, and you can divide both sides with e to the j omega t. But here now we have our favorite convolution property, so we can do this even smarter. Okay, so yeah, we know that by the convolution property, big Y is just big H times big X, and yeah, I guess let's go this way. So we have our differential equation like this, and what we do is we go to frequency domain. Okay, So frequency domain, then Fourier transform is linear, so summation here, summation AK is so summation AK, and then so next thing happen is the differentiation, go to frequency domain is something very easy. So when you differentiation once, you just get J omega. So differentiate K times, you just get J omega to a K. And then your Y goes to big Y. And a similar thing happen here. So summation B J omega to a K, X of J omega. Okay. And now frequency domain of LTI system is very easy. It is a simple relationship. Your output big Y is your system function big H times your input big X. And so then you can divide X for this side. So your big X is big Y divided by big X. Okay? And you can just read this thing from here directly. So divide big X to this side. And yeah, you notice that the only dependence on Y and X are here. So you have big Y here and a big X here. The differentiation just becomes multiplication with J omega to a K. And yeah, how should I say? I guess the decoupling actually happen is the Y here doesn't depend on K, right? Or the summation on K is only concentrated here, and the summation on K only concentrated here. In a time domain, you have your dy dt to a k, dky dt to a k, and this is also different terms depending on k, but not a k decoupled with your y, just a multiplication of y. And the bottom line is, then you can move things around, then you have big y divided by dx, you can directly read from the equation. It's this summation bk j omega to a k divided by summation ak and j omega to a k. So you have a really easy equation here. And so yeah, so you see this differential equation, then you can basically just write down its system function directly, just read the coefficients. So let's see an example. Easier. So yeah, you have our differential equation. So dy, so second derivative, then plus 4 dy dt and plus 3y, and equal to dx dt plus 2x of t. And as we say, we can read the big H just directly from the coefficient here. So we have dx dt, so we get j omega here, then plus 2 divided by j omega squared plus 4j omega plus 3. Cool. We know our system already. Okay. And then if we want to know the system a little more, so we have a big H, and we can calculate our small h. And yeah, so the dumb way to do this is you look at big H, then you do your synthesis equation, you integrate over with your e to the j omega t, and you can calculate small h, but it's quite hard. And so this is where, once again, we use our partial fraction expansion. This is why we say that's very important, because every constant coefficient differential equation is going to give you this rational function on j omega. And you get this rational function on j omega, then you can always do this partial fraction expansion. Yeah. So you can always do partial fraction expansion on your system function, and you get this constant times 1 over j omega plus a terms. And here we have a nice number because we design our system in big nice number. So the x squared plus 4x plus 3 is x plus 1 times x plus 3. And so you do your partial fraction expansion, and we set our number nicely, so you get 1 over 2, 1 over 2 here. Anyway, then you get those two terms. This is the thing we talk about, is 1 over a plus j omega thing. And we know their inverse Fourier transform is going to be this exponential decay. So we get 2 exponential decay, 1 over 2 e minus t u of t, and 1 over 2 e minus 3t, 3 from here, and the u of t. So yeah, we get our system. We will get our time response over our system. Any question? Quite nice. And yeah. Then the other thing you want to solve about this system is probably it's no differential equation related to some LTI system. But maybe more practical thing you want to do with your differential equation is you have some input signal and what's the output signal. So obviously we have our impulse response and you have our input signal, you can do convolution. But here we have some signal in nice terms, so we can do some other thing again. So we can do this in frequency domain. Okay. So our signal once again is this exponential decay function, and we go to frequency domain. Is our favorite one over j omega plus 1. Okay, so it's another rational function. And once again, remember in the frequency domain, our system is going to be big Y equal to big H times big X. And we have this big H that can easily read out. And then we have a rational function times a rational function, you get another rational function. Okay. Now we can solve this, the small y from as the inverse Fourier transform of the rational function, and once again you can do this partial fraction expansion. And here, because you have these square things, so the partial fraction expansion is actually more complicated. So let's call this, yeah. So because you have a square here, so just like we have the example where we have the square and that's just a square, but now we have a square times another thing. So actually we have 3 terms. So instead of just square term, then we also have this linear in j omega plus 1 term. Okay. So yeah, so that's what will happen. And now there are 3 terms. J omega plus 1 and j omega plus 1 square and j omega plus 3 corresponding to 3 term here. And then you have 3 constants here, and you can prove for the search by multiplying those together and then compare with j omega plus 2. And here we just state the result. Hopefully we didn't make a mistake. And anyway, so you get a partial fraction expansion of your big Y here, and they are basically exponential decay except for the square here, you get extra t here. You can kind of read off the table here. That's why we have the table here. Okay? Yeah, so have a square term, and you get this t e to the minus at. And yeah, then we solve the output signal of our output signal of this differential equation. Or I guess the more differential equation term, we solve the initial value problem. Yeah. When you have some driving force, that's the exponential decay. So any question about how to solve a differential equation? So yeah, you're probably going to see this or some example of this in your homework, also in your midterm. Okay. And yeah, get yourself familiar with the partial fraction and expansion. Oh, question? SD， 等一下，你说的 S 是什么东西？ 你说如果 input 是很 divergent 的东西吗？应该是这样，对。但是我们应该是不会丢太奇怪的 XOT 给你。我想想看，对啊，如果 XOT 的 Fourier transform 不 converge 的话，那就对啊，就不会用，好像也没什么办法。对啊，那你就没有 big XOT， 那就不太能用。对，但是如果XOT 那么糟的话，不过 Y of T 其实还是可以写的，所以不能说就没有 Y of T。对 ，OK。Any other question? Okay. If not, then let's have a summary. So summary actually means lots of things. I think a better summary or tables. But yeah, so for the transform is really nice. And the equations are here. I guess those three equations are very important. So we have our analysis relationship, analysis equation here, and the synthesis equation here. You should memorize those two. And also, this really nice convolution property because they are extra important because they tell you a lot about our LTI system. So, our LTI system in time domain can be viewed as your impulse response convoluted with your signal. And if you do Fourier transform this thing, that become then your output signal in frequency domain can be viewed as your system function, just multiply with your Fourier transform your input signal. Okay. And that's it. And homework, the first part of homework that should be due next Tuesday, and the other 5 will be due next Tuesday. Question? Or we only have 3 minutes, so we can stop here. Okay. Then let's stop.
但刚才就是，如果说就是给的那个 input 不要太奇怪的话，是不是就是通常如果解到高阶的那种那个 differential equation 的话，就是通常都是用那种方法。
高阶的 differential equation 什么意思？
就是
你说解这个 differential equation？
因为我在想说它后面的，因为之前就是微分方程后面都是一定是比较漂亮。我想说这个是不是，如果说只要 input 不要太奇怪，它其实是一个蛮万解的东西。
对啊，这看起来蛮万解，不是吗？虽然说解的这么漂亮是需要比较特殊啊。我们这里是直接就什么积分都不需要嘛。
对。
这里这么漂亮是因为你的 x 很漂亮，你的 x 它 Fourier transform 是个有 rational function 嘛，所以乘完还是 rational function， 你就直接 partial fraction expansion 完，然后就结束了。那如果这里是个新的东西的话，那你一样可以做出 big y 嘛 ，big y 反正你就把 big h 乘上 x 的 Fourier transform。但是那你在做 inverse Fourier transform 回来的时候，可能就比较难，就是你可能就真的要去做积分这样。对啊，我在说的。
老师，那有可能就是我可以写出它的频率，但是不是也有可能是我写出它的频，但是我没办法写出它的时率，就是有可能会有。
应该不会吧？我想想看，你说如果不 converge 吗？我不太确定，感觉有点奇怪才会这样子。如果没有 convergence 的issue的话，应该都可以啊，因为就是你 equation 总是可以写嘛，就这个 equation， 对吧？你总是可以这个 equation， 然后你就硬是积分嘛，然后积分如果 converge 的话，就是理论上是都可以算的嘛。对啊。
了解。 老在前面，
对。
是靠多久？但是你在计算系统做日程，所以你应该就要他们的程序，都还能这个